In this worked example, we're taking a look at the hydrostatic pressure equation, and it is one of the equations that is given on the list of formulas. So as you read through it, hopefully you can pick out the helpful equation, that hydrostatic pressure equation, and solving it. But even with that equation in mind, I really think that this is the type of question that's, a little bit tricky. And it's easy to oversimplify it and to, put some numbers down into the equation and calculate one of the choices that's up there, but it's not the correct one. And so this question reads, the density of air on the Earth decreases almost linearly with height, from 1.22 kilograms per cubic meter at sea level to 0.74 kilograms per cubic meter at an altitude of 5,000 meters. So that kind of makes sense that the air is more dense down at sea level, and then it decreases as you go up. It says almost linearly, which I think is important. It is important in this calculation. Atmospheric pressure at the Earth's surface on a particular day is 100,000 pascals. You may recall from chemistry, 101 kilopascals is the value we typically use for atmospheric pressure. The value of G between the Earth's surface and an altitude of 5,000 meters can be considered to have a constant value of 9.7 meters per second squared. So we're used to using G equals 9.81, but the language of this sentence is a big clue in terms of how to approach the rest of it. It really is. What will be the atmospheric pressure at an altitude of 5,000 meters? I think it's easier to make sense of this to draw a 5-kilometer cliff. So there's 5,000 meters, 5 kilometers, and I want to know the pressure here. Okay, down here is sea level, so there's my sea. The way to approach this calculation is to really understand what that hydrostatic pressure equation sort of tells us, or how it was derived. So you may recall that we derived an equation for pressure that is the density times the acceleration due to gravity times the height. And that height is the height of like all the air or the fluid above the point you're measuring the pressure to. We derived this equation by considering like a box of water, you may recall, and say, oh, this water has weight, right? And then force per area, and you sort of make some substitutions, right? And so if you want to see the derivation of this equation, just click on the link above. In order to determine the pressure here, the strategy that students should have in mind is to subtract away the pressure due to all this air beneath your feet. Right? If you're standing on a 5-kilometer cliff, you're not feeling the pressure of all this air. Okay, so you're only feeling the pressure of the air above your head. That is critical to understand here. One of the very first things that I would do to avoid making mistakes, because I hate making mistakes when I feel like I understand the physics and then it's like, oh, it was just a tricky question. I made a careless error at the end, or I didn't, transfer something over correctly. Because like I said, there's plenty of chances to calculate sort of the incorrect answer along the way and be so satisfied with your calculation that you're like, oh, look, that number is there. I'll choose that. All that work for nothing. So the very first thing I would do is take this 100,000 pascals and realize like that's the pressure, but I need to subtract away from it some other pressure, okay? Namely the pressure of all this air right here. And that's what's going to get me to my final answer. Like my answer is going to be taking this pressure and then getting rid of all of this. And so my work now is to use this equation to calculate the pressure of this 5,000 meters of air that's beneath my feet that I need to subtract away from it. I like to sort of roadmap the solution beginning with the end in mind. Like what's the final step in my calculation so I don't forget it? Because you can calculate a pressure here, look at an answer and go, oh, there you go. And it's wrong. All that work for nothing. So you kind of want to keep in mind the critical last step, if you can find it. And again, sometimes we read through a question and the more physics you know, it's like, oh, I kind of see the path to the solution here. I know I have my work cut out for me. I have to calculate things along the way and so on, but I kind of see what the final sort of solution is going to be. It's pretty clear what value we should use for G, right? So, okay, we want to calculate, remember, the pressure of all this. So G, they say, and again, this is such a good clue, this sentence here. Let me read it again. The value of G between the Earth's surface here and an altitude of 5,000 meters, which is like where we want to know the pressure, can be considered to have a constant value of. Okay, so it's like between here and here, like we know it's 9.8, but they're like, oh yeah, but it can vary. It's not a true constant depending on your height above sea level or your latitude even, right? Because Earth isn't a perfect sphere either, right? So there's, G is slightly different places, but close to Earth's surface, it's about 9.8. 9.81 is what we like to use typically in this course. And so we need to now consider, like it's pretty clear also what the height is going to be. Okay, there's 5,000 meters of air above our head right here. Okay. If you just simply say, oh, it's the pressure is rho GH, this is the density at the point I want to measure, 5,000 is a height, and you plug in 9.7, you will incorrectly get choice A. So if we just did a sort of a naive calculation, we said, okay, this is the density at the place I sort of want to measure to, 0.74 times 9.7 times 5,000. That gives me 35,890. And so if you calculate that, you've made a mistake. Okay, that's not the way to approach this, because again, the 5,000 meters isn't the height of the air above your head at the point you want to know. It's the air below your feet, and you're not feeling the pressure of that. A pressure gauge here wouldn't feel the 5,000 meters of air there. So that's not the correct answer. Okay, to just take this density. A student that does that is it's like saying, oh, they told me this, and that's just extraneous. I don't need to consider that. Well, you do. And again, this sentence is a clue. It's like saying, hey, between here and here, we can consider it to be this. Well, what can we consider the density to be if it decreases almost linearly from this to that? It's like down here, it's 1.22. So should we use that value? Up here, it's 0.74. So should we use that value? Or it's like going to decrease linearly, almost linearly. The word almost is like better, accurate science. The troposphere of our atmosphere, the first 6 miles, contains 75% of the atmosphere. Okay. And then it sort of trails off from there. So it is true that like most of the atmosphere is sort of close to the Earth's surface in the troposphere, where most of the weather occurs. In the stratosphere and the mesosphere, and by the time you're at like the ionosphere, you're in outer space where basically the density is zero, very close to zero. But almost linearly is giving you permission to do something with these numbers so that you can substitute in for density. And does anybody know what we should do with those numbers? That makes sense to plug in here for density. So we can calculate the pressure of all this air. What's the density of the air? 5,000 meters of air. So I'm going to use 9.7 per G. The units are all good, right? Meters per second squared, meters. So we're going to get, newtons per meter squared or pascals of pressure. So there's no conversions here, right? Everything is, kilograms per cubic meter. It's all the SI units. So I'm going to kind of tidy up my calculation and just drop the units. But if you included them, you would find indeed that you get the newtons per square meter or pascals of pressure. So that's the good height. That's the good value of, G. But what is a good density to plug in? What do I have to do here? Who sees it? If you see it, leave it down in the comments below. If you're lucky enough to be in person right now, in class, and not watching this on YouTube centuries in the future, you might know what to do with these numbers. Call it out if you do. There you go. Don't forget to like and subscribe. The merch is coming, guys. It's a matter of time. Yes, whoever said it, take the average. We're going to take the average. Because, like we can't plug in 1.22, we can't plug in 0.74, but it decreases almost linearly. Well, that's kind of like, well, I'll just take the average of it, right? It's the average density there. Anybody know how to calculate an average? Heard somebody say, add up all the values and divide by the number of values that you added. That's correct, whoever said it. And so if you do that for these two values, you get, 0.98. 0.98, okay, that's the average density of the air that we want to know the pressure of. Once we do this calculation, 0.98 times 9.7 times 5,000, we get an answer of 47,530. And again, you don't want to be so satisfied with that calculation going like, yes, I calculated the density correctly. I plugged it into my hydrostatic pressure equation. Choice B is incorrect, right? Because remember what we did up here. We outlined sort of the roadmap for the solution. We said, if the pressure on a particular day is 100,000 pascals, but I'm standing 5 kilometers above Earth's surface, I'm not feeling these 47,530 pascals of pressure. They're beneath my feet. All that's due to the weight of all this air. Right, I'm standing up here. So the last final step is to take that 47,530 and subtract it from 100,000. So my calculator, I'll just make that value negative, add 100,000 to it, and I get 52,470. Sort of double check, I reread the question. What will be the atmospheric pressure at an altitude of 5,000 meters? You kind of double check everything, feel pretty good about it. Like, nope, wasn't that one, it wasn't that one. Probably a way to calculate this one too. That's obviously incorrect. Maybe if you just used like the 1.22 instead of the 0.74 or something. But C is the correct answer, right? And so that, again, it's using the hydrostatic pressure equation, but it's kind of a tricky way to think through it, right? And it requires an intermediate calculation along the way with average density to plug that in. But it's helpful to sort of think through it like that and to really talk your way through these calculations and say, like, as I plug in these values, what am I really sort of calculating? If I put a pressure gauge here, what am I measuring? This has been another worked example with Dr. Schleif for the midterm review, and we'll see you next time.